29. January 29 to 31. So 15th is the last date for submission of the paper. In case you have not submitted, I encourage you to submit. Even if you 2-3 days of delay, please let me know. Come on,
I'm just looking about the level of battery. It's quite low, but I think it's functioning. Yeah. But not a problem. I think it's yeah. I think this is okay. Yeah. Yes, I can use that one. Yes, okay. But if the battery dies, then I'll change that one. No, no, please take it care. Because it's I can put this one also here, and it's not a problem. Shall we start? Okay. We start? Yeah, we start.
So we start for the day 5 of the GIAN program, and today we have two very important lectures. Very important because quality assurance and quality check, they are the integral part and in a very important part of the any measurements. So not only it need not be radioactivity, it is any measurement. And in radioactivity it is more important because you are measuring extremely low levels.
Mm-hmm.
So you have to be, when you generate data, you have to be extremely cautious and you should give adequate importance for quality assurance and quality check. Quality assurance and quality check, you have to participate in intercomparison exercises and measurement with as many labs as possible, repeated measurements. And for every data, you have to come out with the uncertainties associated. Mm-hmm. So Dr. Roy will be explaining those aspects in more detail. So, Dr. Roy, please.
Thank you, Karuna. Yeah. So, good morning once more. Are you okay today? Fine. Do we have some problems here?
No. It's okay. Yeah.
All right.
We try to reduce the noise level.
Yeah. Okay.
Yeah.
Yeah.
So now it is much better.
Yeah. It's okay.
Yeah.
So, as Karuna said, we are talking about quality-related issues, and you might think that this is quite boring area in measurements, but I'm sure that it is one of the most important things when doing laboratory measurements, and also when you are doing scientific research. Because if your research has bad quality, so what would happen then? Nobody believes you in those cases. All right. Let's go. I will move this one here. Okay, these are the contents of the presentation. So what is the difference between quality assurance and quality control? Quality management in a laboratory, qualified personnel, working practices, equipment stability, for example, laboratory information management system, LIMS, uncertainty estimation, very shortly in this case. In the next presentation, I will consider this part more detailed. How to prove quality of the analysis methods and how to prove quality excellence. So just now we are not talking about technical things. We are now a little bit, how to say, higher level. All right. What is QA/QC? I took this information from this site. Okay, what is quality assurance? Definition here. It is a set of activities for ensuring quality in the processes by which products are developed. In your case, the product is activity of a sample. However, quality control, it's a set of activities for ensuring quality in products. The activities focus on identifying defects in the actual products produced. So I have to say you that I didn't understood. If I look at only this definition, it's difficult to understand what's the difference there. It's better to have some examples. So here are some other points or differences. For example, here, it's a tool. Quality assurance is a managerial tool, whereas quality control is a corrective tool. I will not go through all these things. I hope you will read these later. You will get all these presentations. All right. There is another VVV site. So what's the difference between quality assurance versus quality control? So quality assurance is a broad process for preventing quality failures. The QA team is involved in all stages of a product's development. In essence, production, testing, packaging, and delivery. In contrast, quality control is a narrower process. It focuses on detecting mistakes, errors, or missed requirements. So this is quite good description about the process. Quality assurance, it's a proactive process, whereas quality control is reactive. All right, let's go on. Perhaps you know that my institution, Radiation and Nuclear Safety Authority, it is testing laboratory. We will be later be as a calibration laboratory. So the accreditation of a testing laboratory proves that the laboratory produces reliable results with the testing methods that are included in its scope of accreditation. The testing method is, for example, alpha or gamma ray spectrometry. So testing is therefore product-oriented and thus it is in the QC domain. So testing for quality isn't assuring quality, it's controlling the quality. So quality assurance makes sure you are doing the right things the right way. However, quality control makes sure the results of what you have done are what you expected. Let's give an example of that. So, if you are preparing a quality manual, I mean instructions how to operate in a laboratory, it is a QA process. However, if you are constantly measuring background of your detector or full fit, half, I mean the peak resolution. So it's a quality control area. I think this is one of the most clearer way to see the difference between assurance and control. All right, quality management in a lab. So it is composed of many things, starting with very high level, I mean quality policy. System should define very well the leadership, who is responsible of what. Quality manuals must be prepared. And there must be a systematic way to collect information related to quality. Of course, you must obey some standards. This is essential thing. Developing a quality system, it is a continuous operation. In our lab, we are always doing that. And of course, high working ethics and culture are part of the quality management system. And in fact, the responsibility is yours. So, all employees must be committed to keep high quality in their own work. Of course, the biggest responsibility is for the bosses or professors. But the main response is yours. I mean, in practical issues. So, laboratory practices require, for example, high-quality personnel, well-defined working practices, good quality equipment. I think you have this kind of equipment here. Appropriate laboratory information management system, LIMS. Uncertainty estimation of the measurements. I think this is more quite routine in your case because you are doing research. You have to validate the methods. And in case of errors and mistakes happen, you must have a policy for that. What happens? Because it's very important to reveal if something bad happens. For us, it's a routine. Really a routine. Perhaps I can say that, okay, now I made a mistake for spectrum analysis, and then we are not looking it in a way that is it you or you that did the mistake. It's not the point. So the point is, what is the reason? Do we have some bad procedures? Okay, Participation of intercomparisons and proficiency tests. It's important. Avanes, how many times per year you participate in intercomparisons or proficiency tests? Around?
We participate in IAE intercomparison exercise every year.
Every year, yeah.
In between, sometimes BRC, the Baba Atomic Research Center, also sends their own intercomparison. It's very rare, but it does.
Yeah.
So, or else, sometimes what happens, this year we are planning to have international radon intercomparison exercise, where samples from around last time they sent it here and we were able to measure it. So, minimum one.
Yeah. Okay. Nice. Also, continuous development of work and working practices, it is important. Now I am talking about you. Good quality personnel. So, elements of competence. You must have appropriate education. When you go first time into the job, so somebody must show you briefing, what kind of things you should do. And after this briefing, the new employee demonstrates his or her capability of performing the procedure. And this is important. Continuous learning at work, and this is a standard thing that is used, for example, in university labs, because their main task is to produce PhDs or Master of Science level candidates, and also job rotation. It's a sometimes very good thing. Motivation and ethics, it's very essential. So your well-defined descriptions of the duties is important. Your position must be determined in the quality management system. And this is important, that opinions of the personnel, it's very important. So if you find out some bad processes in the lab, then you have to tell it. You have to tell it to your bosses or professors or directors. And the information flow, it must be active. So if you see some errors in your procedures, then you have to tell it. But of course, the role of supervisors is important. So the typical education in our area, it's a chemistry of physics. We have to understand measuring technology and quality and knowledge of the quality management. So the supervisors, they have overall responsibility for lab procedures and final results. About working practices. So, quality manual or other documentation should cover all working practices. So there must be guidance of the work. Safety at work must be considered. Cleanliness, so that we can avoid contamination or cross-contamination. precautions for handling of chemicals and equipment. Environmental conditions must be good too. So, as you have here in this laboratory, there are separate rooms for sample treatment or pre-treatment, measurement equipment, and analysis. So it's very important, especially in radiation measurement area, the background must be as low as possible. There must be a backup system for electricity. Do you have this backup system here? What about the lab?
Yeah, this is for
This is, yeah,
This is actually 3 kV system.
yeah,
And we have a 7 kV system
Yeah.
upstairs. So we get around 16 hours of backup for low load.
yeah.
And if it is high load, around sometimes during the thunderstorms.
Which you can explain this to whole.
So during thunderstorms, we switch it off in the night and remove the plug so that our systems do not get affected by the thunderstorms. Because even I think it's a very big problem here. Systems don't go shut off. So that is one of the systems that we have. And for the first floor, it is completely separate systems. And then to back up this backup, we have generators. So suppose power does not come within, like let us say, 10 hours or 12 hours, in an unfortunate condition, we can switch on our generators.
All right, thanks. So one point is also that we should, or labs should have continuous monitoring of humidity, temperature, dust, radon, etc. in the lab. For example, this is one part of our lab. This is a gamma ray counting room, and we are constantly measuring, for example, these things. This is also quite important thing that we should not allow all persons to go to lab, because they might not know how to behave in the lab. It is one point. There are several other things that must be taken into account. So it's a more or less security-related thing. And the biggest point is this: everybody must follow instructions. Equipment stability. So regular follow-up is necessary. I mean, detector background, energy resolution, and efficiency. Blank samples should be measured regularly, and following up the performance of the analysis method, it's necessary. And also control charts, including warning and action limits. They are they should be present. Acceptance criteria in these cases are normally set to 2 sigma or coverage factor to 2 as a warning limit and 3 sigma as an action limit. So, for example, in this case, our chemistry team is monitoring Quantulus background, the scintillation spectrometer, this one. So this axis is here, time, and this is count rate. So the background should stay normally between these areas. However, if the backgrounds go there, it's a warning. Perhaps they should do something if the background goes there. And if the backgrounds go there, then they really has to do something. What's going on in your detector? So the most important thing is to know the operation of the equipment. You need to know how the equipment functions. This is the key issue. All right. LIMS system. Some of its characteristics. It should be well described and documented, easy to use and flexible, extensive enough but fit for purpose. It may contain the whole chain of sampling, sample processing, measurements, analysis, and finally reporting the results. Avanes, can you tell all of us what kind of LIMS system you have in your laboratory? I mean laboratory information management system.
We don't have a centralized system as such, but should go by the slide, basically. So the normal practice everyone does. We take care of all the field conditions, we take out all data, we write down it, we note it down, and a copy of it is forwarded to the reporting manager and everyone who is related to it. So the first time is have a laboratory manual, one which is called as GIAN manual, and also we take manuals from other reputed like Kellogg Soil Survey Laboratory and Environmental Monitoring Laboratory (EML) manual, and we have made our own set of manuals for each data or each analysis. And then once the data is generated, set of results, one of us is going to do it separately so that we can check the quality of the data, and this is sent to the reporting manager and approves it whether this is good or not. So this is kind of a practice we hold, but this is something new for me.
All right. Okay, let's go on. So following the whole analysis process in real time, it is essential. So it's the role of the LIMS system. It should also contain quality control issues, should be well protected, I mean data security, and its maintenance should be straightforward. I will show you some things how we do or what kind of LIMS system we have. We have a system called as NAMIT. It just made web-based software to manage data flow during the fuel analysis chain. So we basically analyze two kinds of samples. So sometimes individual companies send us samples, and they are saying that please analyze the results, and then we do that. But of course, we are doing sampling by ourselves, of course. So this is included, this phase in our LIMS. Sample processing system is there. Measurements, of course, are there. Not only gamma ray spectrometry, but alpha spectrometry, and for example, ICP-MS, mass spectrometer. Spectrum analysis is included that system, and also reporting. So it's in fact very big system. So, and the analysis process is, we can follow it as a chain. So there is a color coding follow-up system. I will show you an example soon. So our system can follow the measurements like this. Here is an example for gamma ray spectrometry. Here are 4 detectors. Detector names are here. The detector status is shown here. This mittauskäynnistä means that measurements is going on in that detector. So we have a sample code. We call it as a NAMIT code. Then the measurement time. And we can see a brief, very small picture of the spectrum that we can very quickly see that, okay, it's really measuring, and there is a spectrum. So this is perhaps the main window of the software. In this column, there are samples, short sample description. For example, the first sample here is air. Second one is milk. So these 3 columns show that which is the status of the measurement. And for example, in this case, this sample is waiting for the measurement. This column shows that is the measurement ready. And if it is ready, then color is green. As I told you previously, we have automated analysis system for the spectrum analysis. And it is this column here. Green means that automated process was okay. However, in this case, something happened. So there is no automated process. And in this case, we have to check what's going on. After automated analysis, we do manual checks for all the spectrum. So yellow color means that we are waiting for the system is waiting for the manual analysis. This is the way how we can follow our detector calibrations. It's a quite complex picture, but in this case, we have a detector known as B3 and a certain source or sample. This is measurement time, and these are the nuclides present in several of our samples. And these are the activities of each nuclide in a certain reference date. And if we are measuring, this is for year 2015, so almost 10 years old. But according to the color coding, for example, yellow means that, okay, you should check the result once more. For example, in this americium case, the true value is 211, but we obtained in the automated analysis 223 becquerels, as an example. Okay, some nuclides has already dead because they are short-lived nuclides. So this is the way how we follow the calibration correction. Let's go to uncertainty estimation. It's in fact quite tedious and sometimes difficult area. Not very easy area, but I'm talking it very briefly. So, relevant thing is that all uncertainty components must be accounted for and quantified. I will show you soon some examples. It requires good knowledge of sources and uncertainties in the sample preparation, measurement, and analysis, and its traceability is essential. So the point here is that a result without uncertainty estimation is not a real result. I mean, in science, of course, in practical life, everyday life, it's not so important. But in science, this is important. And you have to realize also that combined uncertainty is not equal with statistical uncertainty. I will explain this more clearer tomorrow. But this is the thing that we report when we report the result of the analysis. This is just a short example. One of my colleagues did this several years ago. This is an example of lead-210 in radiochemical separation. So there are different things. This axis is uncertainty in percentages, and these are the things that affect uncertainties. For example, measurement, basically it has an uncertainty level of 6%, but it may vary depending on the case. Weighting, by using scales, for example, it usually has a low uncertainty. Pipetting, in fact, I don't know these two, what's this intron ether, but about the tracer nuclides, and the total uncertainty is around, in this example, it's around 11%. Another example, typical uncertainties in gamma ray spectrometry. This concerns coverage factor of 1, which is in fact the same thing as sigma is 1. Okay, typical peak area evaluation uncertainty is around 0.1 up to 30%. In Stuk, we have decided that if peak area uncertainty is greater than 30%, then we do not report that nuclide. We report, for example, minimum activity level in that case. Background may sometimes have a big effect. Full energy peak efficiency 0.1 to 15%, it depends on the energy. Standard sources, their activities are usually very well defined. Gamma ray emission probabilities in a nuclide library, they are usually very well known. However, in some cases, especially when the emission yield is extremely low, it may be up to around 20%. But these are just examples. Okay, this picture is really bad from the visualization point of view. But what I did around 10 years ago, I identified in gamma ray spectrometry many uncertainty components influencing the results of our measurements. And the measurement is done with a calibration source. So the first source here is probably lead 210. Second one was americium 241. Then it goes to the highest energies. This is yttrium 88. These two peaks here, or spots here, they are for cobalt 60. Let's go this case here. So, what happens in the case that if I have a detector here, this one, and I put the source not in the symmetry axis, but it has off the symmetry axis, very small. Distance plus minus plus minus 1 millimeter. In that case, the effect is not very big. Okay, if you go quite top, this means that we do not exactly know what is the sample height. I assumed that the sample height varies plus minus 1 millimeter. Very small, in fact. But the effect of the result is very big. One of the biggest uncertainty components. And in this case, it's a sample elemental composition. So you can see here that, so this number is uncertainty in percentages. You can see that in very low energies, you have to know sample elemental composition to get good analysis result with small uncertainty. And then there is one very complex thing, which is this coincidence correction and its uncertainty, because determining coincidence correction it's not very easy. So there are some nuclides which don't have any coincidence correction, such as cesium-137. So its value, I don't know what is the spot here. Maybe it's this spot. Its value is, uncertainty value is practically 0. But for example, cobalt 60, it has a coincidence correction. You can't see it very well here, but it's this. So the total combined uncertainty, it's this kind of effect for these nuclides. So later, please look at this picture. It is a very bad picture because many components are there. It's difficult to read. But if you follow it, you can understand something more if you look at it very carefully. All right. How to prove the quality of your analysis methods? There are several ways to do that, but intercomparisons or proficiency tests, they are the things, most relevant things. So intercomparisons between different labs. It's a good way to prove quality. Of course, in the case if you have successful results or participation. But in this case, the result depends on the quality of the participating labs. But these proficiency tests, they are normally done by primary laboratories. These primary labs perform or do the samples very carefully. They do many analysis methods in reporting, for example, activities of the nuclides present in the sample, but also other things, elemental composition, etc., etc. So they are very high-level labs, and their results are, in general, you can keep them as correct results. So the result does not depend on the quality of the participating labs. So the sample contains known radionuclide activities with well-estimated uncertainties. But sometimes other issues than the activities are also considered. This is our case. Avanes said that they are participating perhaps once or twice per year in inter-comparisons or proficiency tests. These are our numbers from 2004 up to 2022. So on the average, we are participating 5 to 6 times per year. So, and this thing, it is written in our quality management or quality manual. It's written there that we have to participate 5, 6, even 7 times per year. I don't now remember the exact number. This is a typical example for us. This is cesium-137, and in this picture, there is a so-called Z-score followed. This is the value of Z-score. Look at here. And these numbers here are the numbers of participating labs. We are located somewhere here. So red colors mean that some labs didn't use very good or reported very good result. However, we have done some mistakes in some cases. So this is not the only case when we got very good result. So this was European Commission organized proficiency test. The sample is mice powder. So this is a proficiency test organized by Comprehensive Nuclear Test Ban Treaty Organization. And these are our results only, and the nuclides are shown here. And vertical axis is the percent of deviation. These red lines, I guess they show the limits. So as you can see here, we are capable to analyze all radionuclides that can be detected by gamma spectrometry. And in one case, this is vanadium 48. There is, I cannot say it's not a mistake. Of course, we have analyzed this, but I don't remember this anymore. So, how to prove your quality excellence? So, it's this process, according to this standard. FINAS is our accreditation body. It's a totally independent body that evaluates us. FINAS also makes accreditation to all labs in Finland in different areas, gravitation, temperature, etc., etc. So, this is a good way to prove quality excellence. So, an independent external body evaluates the quality system and gives statement for accreditation, and this is the statement, or a sum of it, summary of it. However, if you have no accreditation, you should still have good management system. You should have comprehensive documentation. You should participate in inter-comparisons or proficiency tests, internal audits, or self-assessments. They are necessary. And a laboratory can request an independent external body to evaluate the laboratory. In Finland, this process is quite costly. I don't know the exact sums, but it is more than 10,000 euros to evaluate us. It's in fact a big process. Internal audits. About in your labs, are you doing internal auditations? Any comments? So I mean that some other units of your labs are evaluating your job. All right, but this is our standard procedure. We are doing this several times per year, and all areas. It also helps those that are making the auditation. If you are the guy who is doing the auditation to another lab, so it's like a learning process. It's a very good practice. So it gives you a look the work from different point of view. The best results are achieved when everyone involved are motivated and the attitude is positive. So it is also important not only the faults or errors. You should also document best practices. So, if you do nothing, you make no mistakes. However, we have to work, and therefore mistakes happen. And human errors, I think they are perhaps the most relevant errors. Indeed. So, a lab needs a policy and procedures that define what to do in this case of errors. For example, if I make an error, I will certainly, in the next lab session, we have one internal lab session once per week. I will certainly, in those cases, explain what happened, and then we think over what kind of things we should do to avoid this kind of error anymore. So it's not a good way to hide the errors. Not a good way. So, in case of mistake, it is important to observe, report, declare, make corrective actions, make preventive actions, and document the case. We are humans and errors happen. That's the case. We have to tailor our processes so that all these things that I explained in these presentations should be considered. All right, this was my last slide. I thank you very much for listening this. This might be or might sound quite boring area, but this is very, very, very important area. I think one of the most important areas. Any comments, questions? All right, if not, shall we have a break? If we go back 11:30, is it okay? Half an hour break? Is it too much? 11:30. All right.
So Roy, I had mailed you last day.
Sorry?
I had mailed you last day about the.
Oh, I haven't read my emails. I will read them when I go back to Finland. Is it okay?
It's okay, sir.
Thank you.
Hello.
Hello.
And I have got 12% efficiency at the end. I have to eliminate when I calculated this. I have to take it from balance.
Don't let me to disturb you. All right, shall we start the next presentation? Dealing with uncertainty determination. As I told you, this is quite difficult area, in fact, not an easy area, but we are scientists. We have to understand this area. Every time when you do a scientific publication, and if there are some measurement numbers, then you have to put their uncertainty estimation. And you have to explain how this uncertainty is calculated. I'm sure that you know why to determine uncertainties. Let's look at the steps of this uncertainty assessment, and let's have an example of it. So, let's assume that a measurement result was obtained by using two different methods, method 1 and method 2, but without any uncertainties. How to assess the reliability of the measurement? In essence, which of the results shown below is more reliable? Any suggestions? Which one? No idea, in fact, because the real comparison is not possible, in fact. Let's assume that we know the uncertainties. In this case, the uncertainty is small. In this case, it is big. The comparison is now much more easier, since the uncertainties are overlapping. But is this difference meaningless? Oh. Let's assume that we are making a calibration source and we must prepare a source with activity of 10 becquerels plus minus 0.03 becquerels. So the results show that only measurement 1 demonstrates the compliance. So these are the benefits. Method 2 might be notable cheaper, but sorry? So uncertainty is larger. Okay, it should be not accurate enough. So there is one word missing, but not accurate enough. Vice versa, only method is good enough, and using method number 2 was the method number 2 possibly lead to increasing costs due to invalid end products. So higher costs might cause if the uncertainty is overestimated. So the measurement results are reliable. In essence, the measurer or developer of the method knows that it is functioning, that the method is functioning correctly, what is critical, etc. The user of the results who do not know details of the method can assess the level or quality of the measurement. So higher risks follow if uncertainty is underestimated. Some other benefits. It gives opportunity to improve quality management and operating methods. It increases understanding of the effects of different components influencing the results. And there may be many different components in the measurements. I will show these components later as an example. Comparison between the methods enables to estimate which method is better and what is the level of accuracy really needed. The traceability chain breaks with a measurement whose uncertainty is unknown. In addition, you have to know dispersion of the measurements, environmental conditions, understanding of sample effects, etc., etc. So, from the point of view of the decision making, the measurement result without stating the associated uncertainty, it is practically meaningless, at least in science. In normal life, it might be different. Another anecdote. With the measurement uncertainty, you get certainty for the measurements. One thing that you have to understand is this. So this regards to the terminology. So uncertainty is a little bit different thing than error. Error is the difference between a measurement value and the true value of the measurement. Very simple. However, uncertainty characterizes the dispersion of the values that could reasonably be attributed to the measurements. But usually we are speaking quite loosely when we are speaking to our friends. For example, we do not use uncertainties. We are using, okay, let's do the error estimation. We are not talking about uncertainty estimation, which is the correct word, in fact. Let's go to see the steps of the uncertainty assessment. So at first, we have to define the measurand. The measurand in our case is activity or activity concentration. We have to define how the measurand is calculated. We have to identify relevant uncertainty components. We have to estimate so-called standard uncertainty of each component. Then we have to calculate combined uncertainty, calculate expanded uncertainty, and determine or report uncertainty budget. Okay, let's look at all these points separately. So what's the measurand? It's activity per sample of nuclide EI, or its activity concentration. Its value is reported with the associated standard uncertainty as follows. For example, in this case, the values are within A minus U or A plus U. Or perhaps A minus U 2 times U or plus 2 times U. Here is so-called coverage factor, which is in fact the same as sigma is 2. This is in fact the model equation, not very complex equation. So, as you know, different uncertainty components cannot be directly summarized as such. No, that way. So the model equation is a function of different input quantities. with different range of uncertainty. For example, uncertainty rates here in the number of counts in the peak it's different than, for example, uncertainty here. So we must identify their uncertainty components and quantify them. It is shown in the next slides. So this is linear model, and it's of the equation, and it consists only multiplications or divisions, and consists quantities with different units. So there is number of counts, time, seconds, here mass or cubic meter. How to combine these? So quite often it's better to use relative values. This equation is, of course, implemented in a software, analysis software, that calculates the value of the measurand. In our case, this software calculating the efficiency, which is FTRAN in our case. It's another software. But it is included directly in our analysis process. Identification of essential components. In the beginning of the identification process, you should recognize all possible components, either if they are relevant or not. This is also important, because it shows that their existence are accounted for. A comprehensive list of components is valuable, especially in the case if some changes happens in the future. I mean, if the measurement or analysis process changes. So previously non-relevant component may later be relevant. So other components than presented in the next slide may become significant. These may include, for example, variation of environmental conditions and drift of the measuring equipment. And human factors may sometimes cause notable uncertainties. These are difficult to determine. I have to confess that I have difficulties in this area, because uncertainties in these cases are very difficult to determine. And how to take into account human error. Very difficult area. Okay, let's look at more about the details. So, according to this equation, the main components are following. Number of counts in the photo peak here. This is usually determined by the aid of the analysis software. Not a big problem. What about data acquisition time? So practically its uncertainty is insignificant. So when I did our uncertainty estimation, I neglected that component. But of course, it is taken into account in the identification process, uncertainty identification process. What about emission yield of gammas or alphas? It should be obtained from the evaluated nuclear data, such as this TDEP LARA application. Sample quantity, here in terms of mass. It is usually measured by scales whose uncertainty is usually very small compared to other uncertainty components. Scales are accurate. I think so. Correction factors, such as coincidence correction, might play an essential role in the uncertainty determination. I think that the most important components, in addition to this, is the number of counts and efficiency. So, how to estimate standard uncertainty of each component? They can be classified into two different types. Type A, quantities are estimated by statistical means and are expressed as standard deviations. Usually these are obtained from measurements. And in this case, standard uncertainty is standard deviation of the mean. Then there is another set of, or type of uncertainties, type B. Uncertainties are evaluated by other means, such as previous experiences, literature data, data obtained from manufacturers, data from certificates, etc., etc. Maybe opinion of a professor is one example. So, in this case, it might be sometimes quite difficult, but there are several distributions. Normal, triangular, rectangular, or something else. At least from my point of view, in reality, there is no clear distinction between these types. The point here is that these must be scaled to standard uncertainties, and how to do that. It is an example of type A determination. Let's assume that we are looking for the precision of a scale to determine its uncertainty. This is a scale, not the one that you are using in your lab. But anyway, so we must have enough observations, like here. There are a number of measurements, and standard deviation and mean value is this one. So standard uncertainty, which is different to standard deviation, it is determined statistically by calculating standard deviation of the mean. And you can calculate it this way. So, finally, this is standard deviation and number of observations. So, what's the difference between standard deviation and standard deviation of the mean? So this is individual, this probability distribution of individual measurement. It's quite wide, of course, as you can see here. This is standard deviation in this case, as an example. So we have 16 observations, standard deviation 20. But the probability distribution of the mean is narrower. So, and you can calculate it like this way here. The correct number is 5. Okay, everybody can see, I guess so. Thanks. So this is type A. What about type B? Let's assume that that estimate of the activity in the source certificate is A, activity of some nuclide. But we do not know the shape of the probability distribution, only upper and lower limits. This is quite typical. Not necessarily in the source certificate, there are a lot of other things. We know only lower and higher limits. So there is a rectangular distribution like this. How to calculate its standard uncertainty? So let's have an example. We have cesium-137 in the source, and activities are between these two numbers. So uncertainty in this case, a standard uncertainty is in this case 10 divided by square root of 3. And these are how standard uncertainties are calculated in different distributions. This rectangular distribution is, I think it's most often used, or this Gaussian shape. So, as you can see, the standard uncertainty is smaller than the uncertainty of how to say, uncertainty of the range. I mean, how to say it well. But I think that you know the point here, so sometimes it's difficult to explain. All right. So, how to calculate so-called combined uncertainty, which you will report in your scientific papers. So, each component must be multiplied its sensitivity factor. I will not consider here more, but it's like a baked-in factor. So it tells you how sensitively the measurement result changes if the value of C changes. It is like a baked-in factor. So first we have to take into account this factor C if there is any relevant one. Then square it itself like this one. Then summarize them here, and finally taking the square root. So this is the result. very easy equation in principle. But how to determine each of these components, it is difficult. The point here is that there is so-called central limit theorem. The set of uncertainty sources in these individual sources, they are distributed in different ways. However, the set of uncertainty sources will approach the normal distribution regardless of the individual variables distribution. Oh, what is the expanded uncertainty? In activity measurement, the uncertainties are usually reported by using expanded uncertainty. It's a very simple way to report. So it's obtained by multiplying the standard uncertainty to the coverage factor. In case when sigma is 1, coverage factor it's practically the same. So usually in a testing report, the value of the coverage factor is 2. So there is around 95% probability that your result will stay within the uncertainty values. Here. Please know that I neglected here the correlations in above mentioned slides. Usually they are not very important, but I cannot go through these things. It's a very challenging area. So, determination of uncertainty budget and reporting. Do you know this GAM? How to calculate uncertainties? It is published by BIPM. And let's have an example of uncertainty budget. In this case, it's a determination of strontium-90 case via Cherenkov counting and modified ICROM methods in Bilberry matrix. All right. So, for example, counting statistics. It's a type A uncertainty. Relative uncertainty is to 2%. And its contribution to the total or combined uncertainty is 30%. Efficiency, type A, 2.1%. Chemical yield, B. Half-life of yttrium-90, B. Half-life of strontium, B. Weighing, B. So weighing is usually very, very accurate process. So its uncertainty is very small. Water content, 1%. So total combined uncertainty is this in percentages. So point here is that you can just sum these numbers here. 2 plus 2.1 is 4.1. This is 3.6. So do not summarize each component. Do it this way. Oh, let's go back. Is this clear? Any questions or comments? Right, let's have an example. How to determine efficiency uncertainty. So I have to confess that I did these calculations several years ago, and it was a very tedious process, really tedious one. It took me at least 1 year. Really? But we will be a calibration laboratory, so we have to understand everything, all components. Okay, so I introduced a new efficiency calculation procedure for measuring environmental sample, and we made a new peak efficiency calibration. Before our calibrations, they were quite good, but the point is that in our analysis procedures, we didn't take into account sample elemental composition, and I felt that how we calculate the uncertainties, they were not well documented. Now they are well documented. At first I identified the components, it's shown in the next slide, and quantified these components. I used mainly FTRAN software. So main uncertainty components are, it's a reference source that we get from National Physical Laboratory from Great Britain. It was a small glass ampoule. Then our chemistry team made the final calibration source in our lab. Then I identified the uncertainties with measurement geometry and the beaker for the efficiency calibration. Then I estimated the peak area uncertainties and of course uncertainties associated with the coincidence correction, as you saw in my previous presentation. Let's look at this list. So what I did in the first phase, I identified all the components that I think that these are the relevant ones. 17 components, and only calibration phase. Measuring a real sample, it's a different thing. And then in this case, there is another other list of components. Okay, first one is gamma emission rate, reported in the certificate. And I have to say that I don't know, is it type A or B, because it was not mentioned in the certificate. However, I know that because NPL is a primary laboratory, that laboratory is doing their work very well and very accurately, I rely on this value for individual nuclides. Uncertainty of radionuclide half-life, it's from the library data, and I don't know, is it A or B type. So this is in fact the same data as Lara shows. Uncertainty of the emission probability. It is taken into account. Then we made, this is the original liquid ampoule. Then our chemistry team made the final calibration source. And then uncertainty of the gamma emission rate was taken into account. Uncertainty caused by the source inhomogeneity. It was not, in fact, not taken into account because it was a water-like source, some acid is there to prevent radionuclide deposition to the walls of the beaker. Then uncertainty caused by elemental composition, we know it very well because there is water and some acid. It's known. And this is accounted for in U1 here. All right. Uncertainty caused by calibration source height. In our case, the calibration source is 2 centimeters thick, so it's taken into account. However, it is quite difficult to measure how thick the sample is, and its uncertainty in terms of millimeters is estimated to be 0.5. Uncertainty caused by the diameter variation of the measurement beaker. These beakers are industrially made, but I cannot measure diameter of each beaker because we are making 2,000 measurements per year. So I just assumed that, okay, it is 0.5 millimeters, the diameter variation. Then beaker bottom, I assumed that the variation was 0.1 millimeter. Beaker wall thickness, 0.1 millimeter. Uncertainty caused by the elemental composition of the beaker. Well, I didn't took this. I took it into account. I identified this possibility, but I was not able to analyze. They are polyethylene, I mean the composition, but I don't know, is it possible that the composition of the beaker might vary? So there is no estimation in this case. And then finally, there is a measurement and spectrum analysis phase. So uncertainty of the source positioning, it's this one. This is the detector, and this is the source, calibration source. If it is not exactly put on the symmetry axis of the detector, it may a little bit vary the result. It is taken into account. In this case, we assume that it's 1 millimeter. So we did the measurement very carefully of putting the source on the detector. Uncertainty caused by the count rate of the peak in question, it is calculated by our analysis software, Unisampo Shaman USS. And these are the uncertainties there. So there are, I took into account also other uncertainty related to the peak area, because I did 2 different ways how to calculate peak area. One way, which is taken into Unisampo Shaman software, it takes into account peak fitting. I used another software which uses this same method as you used here, the ROI analysis. And then I took this into account in a comparison. I don't show it here. The effect was not big, but I found an effect. And uncertainty of the waiting time correction. uncertainty caused by the counting correction during the measurement, uncertainty of the coincidence correction. It is obtained by Unisample Shaman software, and in fact, I don't know, is it A or B type. But our software takes it into account. So, in fact, this was a tedious process. But now I understand what's happening in our measurement process. And you should understand that too, if you want to report qualified results. Is this why my file? Is it dead? I have to change. Batteries are out of order. Let's put this one here. In this way. I will put this one here. Yeah. All right. Now it's on. Changes. Sorry about this. So let's have an example of some of the uncertainty components. For example, coincidence correction. It's a difficult area, and I thought that how to estimate the uncertainty of the coincidence correction. I decided to use 3 different software. The first one was our analysis software. Some nuclides don't have. This is lead 210. This is americium. This is cadmium something. This is only a short list and just an example. But for example, in this case, this was, I guess, cobalt 57. This USS software gave this correction. Then I used FTRAN software, which is able to calculate coincidence corrections. It gave this number. Then I used a full Monte Carlo software known as GESPECOR. It gave me this value. This is the final value and relative uncertainty, this one. In this case, I don't remember the nuclide. I should have put it here in the left side, but the uncertainty component is 2.26%. So this is one example. Another example is here in the left. This is the effect of the measurement beaker bottom variation to the peak efficiency uncertainty as a function of energy. So assumed thickness was 1.35 millimeters plus minus 0.2 millimeters in this case. Horizontal axis is energy starting from 5 kiloelectron volts, and this is the uncertainty in logarithmic units. This was calculated by using FTRAN software. I learned a lot if I used this, or when I used this FTRAN software. It's a very good learning process. And this was the result. In most cases, the beaker thickness, especially at higher energies above 50 or 100, the effect is very small. But if the emission energy is very low, then the beaker bottom thickness variation is notable. Took into account all of components mentioned in the previous slide, and this is the result. So efficiency uncertainty for the beaker is calculated as a function of energy like this. So in fact, there is no physical meaning. It's just a fit that we made. Why fitting? The point is that we are analyzing different nuclides. For example, if a nuclide stays here between these two numbers, we have to know the effect of the nuclide emitting radiation in this energy. That's why we used fitting. All right, I think there is one more slide, and it is this one. So I took this picture from this application. Energy is in this axis, emission energy, and this is the efficiency deviation. And the point here is that if you are measuring stones, for example, there are different kinds of stones. How to know its answer, elemental composition? Well, you can use, for example, scanning electron microscopy with elemental analysis. It is possible, but quite tedious. But the point here is just to show that in these cases, I think that in all these cases, the density was assumed to be the same. I think so. I haven't checked it. But this is only the effect of elemental composition. So, as you can see, it might cause a lot of uncertainties in low energies. In higher energies, let's say above 100 kilo electron volts. This is for gamma ray spectrometry, of course. There is no big effect. In normal cases. However, if you are analyzing very dense materials, for example, I have analyzed once a gold sample in our beaker. Then I found that, okay, the results were wrong. If I did our standard method without taking into account the composition, and results were wrong, below the energies of cesium-137, below the energies of 600. And the point is that the density of the sample was around 8 or 7. But in typical environmental samples, you can use the limit of 100 kilo electron volts. Above that, the effect of elemental composition is not very big. In our case, when we analyze very many different type of sources, I was thinking what kind of or how to do our analysis, because we are usually analyzing lead 210, and I think it's the first one. I'm not sure, I haven't checked it. But the point is that in that case, in the lead case, the composition has a big influence. And we are measuring meat, we are measuring milk, we are measuring building materials with higher density of around 2. We are measuring all kinds of things, and how to take into these composition variation into account. But fortunately, I have a student to work, to did the dirty work. So he did his Master of Science thesis, and he checked, he made a literature survey. What's the composition of, elemental composition of milk? What's the composition of meat? Everything. And we grouped compositions in 3 different groups or classes. And if we analyze, for example, very dense materials like construction materials, I mean practically soil, then we use this group 3 uncertainties in the analysis process. So please remember that in each analysis we use this FTRAN software, and we take into account all uncertainties in each measurement, and automatically. And we can get out uncertainty budget also automatically. All right. I hope that you understood even a little bit of this presentation, because there is some dirty mathematics. But let's do some homework and study what I am talking about. So any comments, questions? Was it too difficult? Remember that this is an advanced course for alpha or gamma spectrometry.
Yes. No, he has started from the basic and he has come to the advanced.
All right, if you don't have any questions, you can later ask me things. I hope that I can answer your questions, because these things are sometimes very difficult. And I can say that when you do it first time, it is tedious, but certainly after that you understand very many different things. All right, thank you very much. What's the time now? Is it lunchtime or? Yeah. Okay, let's have a break.
Yes.
Thanks.
One practicing on have a interaction with the ERC for Okay. Professor Ishri, you didn't go?
No, sir.
So there is a sample ready for counting. And about gamma spectrometry, I think yesterday you were asked to, have you kept the sample for counting yesterday?
Necessity.
So you want to take the counts and calculate it?
Yesterday we took some other spectrum.
Already.
That is doing.
Yeah, all this show. Yeah. So it's up to you. Whatever you want to do, you are free to do. And if you want to do new counting, but you have an idea now how it is done, and practical session followed by excellent lecture from Roy. I have you are through with the alpha spectrometry now.
Revision.
Eh?
Revision.
Anything new you want to go today afternoon, you are most welcome. Or if you want to stay back after the session tomorrow, you are most welcome to come do that tomorrow also.
Send it to me. Last time after this training was over, within 1 week or at the end of that week, we got the no. Last time. After that, it is not valid. It's got to download.
ಎರಡು ಕೊಡ್ಬೇಕಾ ಮೈಕ್
ಮೈಕ್ ಕೊಡ್ತೀನಿ ಇದೇ ಕೊಡಿ
ಕೊಡ್ಸ
ಮೈಕ್ ಕೊಡ್ತೀನಿ
ಕೊಡ್ಸ
ಬರ್ಚಿ ಇತ್ತೆ ಬರ್ಚಿ ಕಾರ್ಯಕರ್ತೆ ಬರ್ಚಿ Yes. All of you are here?
ಲೈವ್
ಇತ್ತೆ ಬರ್ಚಿ ಲೈವ್
ಕೊಡ್ಸ
ಬರ್ಚಿ ಇತ್ತೆ ಬರ್ಚಿ ಮುಗ್ಗರು ಹೋಗಿ ಬಿಟ್ಟಲ್ಲ Okay, good afternoon everybody.
Those who have yet to take activity come to HPG. Those who have completed the gamma spectroscopy business and is waiting for the first batch who came to the HPG. Please go to the first floor, but wait for 10-15 minutes for Bharat sir to come. Okay, once he comes, he will take you there, and it's just another like what 1 hour process, 1 hour, 1.5 hour thing. Okay, so here I think also for you to take activity, it does not take much time. You just have to take activity, and I'll come here and I'll review your answers. Okay, is that fine? So we will move. Yeah. Okay. Idig.
We are complaining. Yeah. Okay. I have only.
You have 4 permanent peak only.
I have only 5 government.
Fine. What are the things?
I will not. You are supposed to find that.
These are not fixed. Because you are zooming
Yeah,
in.
you can remove the R.
One more problem. That is this side. Not this. Window.
He has only 5 answers first. Among 12, within 12, you will find.
I found self before.
You have to find which radionuclide and what is that.
But before we have to no, first we have to give.
You take it as Background actually was ample. He must have done, but it's very less. Very less. Okay. Yeah. I'm not aware. Avanish and Vaishak. The thing is, I'm not very. No, we are on 7.
பின்னாடி வரணும். That is X-ray.
45.2 ಇರುತ್ತೆ. Second relative. Count area வந்து 197.
Area வந்து 120.
197 தெரியல சார்.
Area under curve 1508.
For that we have to move this ROA.
This ROA ரெண்டுமே மெர்ஜ் ஆயிருக்கு. delete பண்ணி விட்டுறாங்க.
இல்ல சார் நாட் மெர்ஜ். கொஞ்சம் ஸ்மால் பண்ணி சைஸ் ரீசைஸ் பண்ணு. அது மெர்ஜ் ஆயிருக்கு. மெர்ஜ் ஆனதா அது ஒரு பிக் அது.
இது மெர்ஜ் ஆயிருக்கு வேண்டாம்.
இது மெர்ஜ் ஆயிருக்கு.
Area under curve 121 வந்து
Same we have to move from here only.
3084.
No, see, that plus is actually
Speak handle is actually not required.
This one is 344.5. 344.5. 356 ல வரும்.
356 னா நெக்ஸ்ட்
352 தான் 356 ல காமிக்குது. காலிபிரேஷன்ல இருக்கு. சென்ட்ராய்டு காமிக்குது அப்படி. சென்ட்ராய்டு தான் காமிக்குது. ஓகே.
Yes,
பைல அனிமேஷன் இது தேவையில்லை. கவுண்ட் கம்மியாக இருக்கு. சரியான கவுண்ட் தேவையில்லை. இது என்னது பெக்கு வந்து 609 தேவையில்லை. இது
That peak is all very small. It's almost like background baseline.
பேஸ்லைன்
964 207 இது தேவையில்லை. இது எடுத்துக்கலாம். இது வந்து 1275. 1275 வந்து கோபால் 60 கிடையாது. 1275 கோபால் 60 கிடையாது. 1508.
சார் 1275 க்ளோஸ் பண்ணிட்டோம்.
ஏன் அதுக்கு மேலே வரல?
அதுக்கு மேல பீக் இல்ல சார்.
பீக் இல்லையா?
இந்த பக்கம் ஏதோ இருக்கு ரொம்ப சின்னதா இருக்கு. இங்க இருக்கிற சின்னதா இருக்கு.
இருக்கு சார்.
கவுண்ட்ஸ் அதிகமாக இல்லை. இதுலேயும் எடுத்துக்கலாம். ஆனால் எபோவ் 1000 வரதை எடுத்துக்கலாம். இதுனா 32.9 is except it is not required. 1 2 5 6 7 fixed.
Out of that,
That 186 வேண்டாம். 186 that is 357.
87 தேவையில்லை. 186 தேவையில்லை.
186 count is very less now.
357.
1 2 3 4 5 6 picks are there. Again இது தேவையில்லை 295 தேவையில்லை this is 790
31,000 வேணும்.
So 45 121.7 121.7 lead நினைக்கிறேன் lead 212 identify peak it will not come
You have to identify based on the energy you have got.
okay this software itself it will identify
Yeah.
It is not within the company rules.
Yeah. The computer actually will do all the work for us, but you have to learn.
you have to find it
Yeah, you have
then
to learn.
we have to go for the new we cannot memorize all those energy terms.
You are not required to memorize. You know?
Okay. So this is simplified that without any SIM card. சார் வந்து சொல்லுங்க எப்படின்றாங்க. அது பெக்குலியர் ஒரு எனர்ஜி இருந்தா சொல்ல முடியாது.
சிஸ்டம் ப்ரோகிராமர் நான் அப்போ வந்து தெரியும் okay then we have to calculate the active sir
Yeah.
Sir, barium 356. Sir,
again
sir,
Active.
sir 356 ஒரு barium ஒன்று இருக்கு.
356 ஆகும் 352 தானே
Sir, having sir 45.4 and 121 and 344. Then next is
352 அப்புறம் வந்து 1
இதெல்லாம் 1000 கிலோ. சொல்லிட்டீங்களா முடிஞ்சு.
First find the activity. Identify.
She is more.
You need efficiency. You need to calculate.
already we know
This is already calculated.
Calculate.
no that corresponding peak we have to calculate nearby efficiency we can take
Only 5.
lead peak 59.5 yeah 2.9
So 45.
this will you know this time RC 3
121. 121. ஒரு அம்பிஷ் பிரச்சனை. அவ்வளோ பார்த்து
1973 into 3 photo 3
127.
3084
You need the gamma in.
in the abundance into 1 to 1 corresponding to 7 to 4
There is a to identify the radium.
344 க்கு பதிலா நீங்க 350 சொல்லுங்க 5 ounce 344.5 into 0.97
This emergency sir. Second was 344.21.
இல்ல
Next one is
இந்த பீக்கு நான் நியர்பை எனர்ஜியோட எஃபிஷியன்சி எடுத்துக்கிட்டேன் ஓகே
பட் அது கவுண்ட் பண்ணிட்டு தானே போடணும். அப்படி இல்லை.
ஓகே
The thing is, please don't keep that in the detector.
Okay.
Because once there is contaminated.
So 1 to 7 is cobalt sir.
No, 1 to 75 cobalt. 1170 1.332 தான் வந்து cobalt. 1 to 75 வந்து it is not cobalt.
Yeah.
I'm saying that 1.1
So 121. 121.
European தானே
344.
344 லாம் 356 தான் பேரியம் 344 352 நினைக்கிறேன் மேபி காலிபிரேஷன் செட்டானாக்க it may be
1 to 7. Cobalt, sir. 1 to 7 1 to 7 cobalt, sir. Yes. But 350.
332 தான் கோபால்ட்.
1 to 75
என்னன்னு பார்க்கணும். அது நம்ம கண்டுபிடிச்சிடலாம். வீட்டில் டேட்டா புக்கை வச்சு தான் கண்டுபிடிக்க முடியும். ஏன்னா தேஞ்சிட்டாரு அசிடிஸ் நம்ம அவ்வளோ எனர்ஜிலாம் நமக்கு தெரியாது. அந்த கண்டுபிடிக்க நம்ம நெட்டில் பார்த்துட்டா
Bromo table.
आराम से நமக்கு எல்கேஜிலிருந்து சாப்பிட்டுக்கலாம். எப்படி நேரமா போகுது. என்ன பண்ணோம் 17 இது வந்து 45க்கு போட்டோம். அடுத்தது வந்து 121க்கு போட்டோம். அடுத்தது
121 அடுத்து 350
352 போட்டோம். அதுக்கு அடுத்தது என்ன பண்ணோம்னாக்கா 1275 1275 என்னன்னு தெரியல. அவங்களுக்கு தெரிஞ்சதான் போட முடியும். அதுக்கு வந்து நம்ம வந்து 0.29 எடுத்துக்கோம். அதாவது 1973 வந்து அது ரெண்டாவது வந்து 3084 வந்து 2.5
எஃபிஷியன்சி சொல்றீங்க.
ஆமா
நியூக்ளியர் பேர் கேட்டேன் சார்.
அது நம்ம நெட்ல தான் பார்த்தோம். அப்படி யாருக்கும் தெரியாது சார். அவங்களுக்கே தெரியும். வேகத்துக்குலாம் பாத்தீங்கன்னா 10 வந்து யூரியா பேசிக்கலாம். நம்ம எப்படி அவ்வளவு பண்ணிக்க முடியாது. எல்லாமே அதான் பார்ப்பாங்க. நம்ம இன்னொரு கண்டுபிடிச்சா எனக்கு என்ன ப்ரமோஷன் தர போறாங்க. 352க்கு வேணா இது பார்த்துக்கலாம். 356ஓட 0.97 போட்டுக்கலாம். எஃபிஷியன்சி போட்டுட்டு நான் என்ன காமோட எனக்கு நெட் இல்ல. யார்கிட்ட நெட் நல்லா தெரியுமா சார்?
காமா எதுக்குடைய அபண்டன்ஸ் சொல்லுங்க சார். நீங்க எலிவேஷன்ல இது இருக்காங்க.
பார்க்கலாம்.
பிரச்சனை
இங்கே இது தேவை.
அது வந்து கவர்மெண்ட் டிஸ்ட்ரிக்ட்ல நீங்க வந்து சொல்றாங்க. ஆமா இன்னைக்கு சார் பாட்டி
ஃபர்ஸ்ட் வந்து 45.2 சார். ஃபர்ஸ்ட்
40 தான் இருக்கு.
அப்படி வேற ஒண்ணும் இல்ல.
தான் இருந்தது இந்த டைம் அது ஸ்கிப் பண்ணிட்டு
45.2 ml
KV.
KV பாருங்க KV 45
சாப்பிட்றது வந்து பார்த்தீங்கன்னா
கொஞ்சம் தான் ட்ரிப் ஆகி
45 இருந்தா போதும். 44, 45 இருந்தா போதும். 80 பண்ணா
இதை சர்ச் பண்ண முடியாது
46 வந்து ஜிங்க் 72. 46 வந்து ஜிங்க் 72. ஜிங்க் வேலை பார்க்கலாம். என்ன வேற என்ன இருக்குன்னு பார்க்கலாம். ஜிங்க் தானே இப்போ காமிச்சிச்சு. ஜிங்க் எனக்கு 72. 121 போட்டு 7 பாருங்க. 1275 1275 தாலியமா 82. What to sound பாருங்க. Madam?
It is not
1052, 1052.
Here
Java
it won't
வச்சு.
work.
Java
Here,
வச்சிருக்கேன்.
here we have scalar.
1275.
In conference room, you can get the network. There are usually what we do is we plot the efficiency graph for that. Efficiency versus energy. And we
You have to find the corresponding.
yes.
That is very big problem. Sodium 1 to 7 value, sodium.
Correct.
Not getting this much only you are. That I know. I know. I know.
No, while 11 is annihilation. The gamma abundance will be very less for a 511 or sodium.
352.
I don't know.
After I found to know I can't.
Potassium, madam, wrong. Potassium. Was it 356 இருக்குமா? இதுல வந்து பேரியம் வந்து
பேரியன் தான் சார்.
பேரியம்னா எல்லா எனர்ஜி மேட்ச் ஆகணும் உங்களுக்கு.
எல்லாமே வந்து இல்லையா?
44.
taken for those energies. 352. 344.
Okay.
352.
நெக்ஸ்ட் போக மாட்டேங்க எனக்கு நாளை உள்ள பார்த்துட்டு 352 இல்ல அது 344
European one. Then next
121 is 152 European.
121 is
152 European.
யூரோப்பியம் நம்பர்
21 European.
186.1 is radian. 226.
121 என்ன
Localized should be there.
120, 86.2 also.
186.
186 radium.
226 radium. 295 is 214 lead.
295.
295.3.
That time that we omitted, no need to type for
We
that.
found it.
Ah,
You will
okay.
take only 1000.
121 is what?
295.
295 is 214 lead.
Like 352? 352?
3. That's our matching, probably some extra.
121
This is 152 European.
That is
52
600.
so we can do the calculation.
779.
ఇదేనా సార్
152 European.
40.2. Plus 40.
So that
No, sir.
but still we I'm a little bit
இல்ல அது
scared.
வேணும் அவங்க வேணாங்களா அப்போ நான் ரெண்டு வேணாம் இருக்கேன் இது ரெண்டு வேணாம்
Maybe even I put up.
You take these values. This is counted on 5/8/2024, and the sample was counted on
ஃபர்ஸ்ட் இது என்ன சொன்னார் சார் 45
24/6/2024. The diagram is here. They have already taken.
No, I call that.
Yeah. Any other questions?
That person was asked for it.
சார் நீங்க சொன்னீங்களா இப்போ
ஆமா சார் 344 வந்து percentage வந்து 26.5%.
26.5% சார்
ஆமா ஆமா. அதாவது சார் யூரோப்பியன் 121 எனர்ஜி இல்லையா அதுக்கு வந்து 28.52.
Store that.
அதுக்கு வந்து 344 வந்து 26.5%. கரெக்ட்டா?
ஏதாவது மாறி
Now we can just do next. Okay.
சோடியம் பாக்கி நீங்க நாளாக பார்த்துருக்கோம். அதுக்கு முன்னாடி இது மட்டும் பேக்
That is 7.63 as well.
6. We need 121.
214. Let it 214. No, let it 214.
Sir, let it 214 350.
350. Sodium, let it 214. That's 7.6.
Sir, yeah,
7.6.
That is 1.6. In the mobile network is what yes. Yes, no, that is good.
அதே மாதிரி நீங்க கொடுக்க முடியாது. ட்ராய் இருக்கு இல்லையா, நீங்க மட்டும் ஒருத்தர் அவனோட வேலையை
I did sing over guys on the past hour. Sodium like efficiency
last one only 1%.
One to 74 வந்து 99.9%. You know, 1 to 75 இல்லையா, actually 74.5.
The efficiency is 99.9%.
சார் 5 கிலோமீட்டர் சார். ஒன்னு வந்து 120 344 கேடுங்க, 352 கேடுங்க.
அது வேணாம்.
அப்ப 4 கேடுங்க போறோம்.
இதுக்கு எவ்வளவு சைஸ்? ஃபர்ஸ்ட் 21.7.
வேற எதுவும் வந்து அதிகமா வேற இது இருக்கலாம் 609.7
By you confirm.
Huh?
26.5.
4.5.
இங்க சொல்லலாம், இதை சொல்லலாம்.
We got 26.5.
610 பண்ணுங்க சார். இன்னொரு 5 கேட்டா
efficiency வர
60 இப்ப என்ன சார், இந்த எனர்ஜிக்கு மட்டும் நம்ம பேக்ரவுண்ட்
இது எப்படி பாக்குறீங்க
எப்படி சார்? இந்த சார் இப்போ வந்து நாம ஒரு இந்த 100% போட்டோம் அபண்டன்ஸ்னாக்கா அதுல வந்து 100% வர்றது நாம அதுதான். இப்போ நீங்க வேற ஒண்ணுக்கு இன்னொன்று போட்டு பாருங்களா. இதுல வந்து என்னன்னா இப்போ வேற எனர்ஜி என்ன கொடுத்துருக்காங்க, 9% கொடுத்துருக்காங்க. வேற எதுனா எனர்ஜி இருக்காங்க. 5 46ல பீட்டா எனர்ஜி வருது இல்லை 90% தான் வரும்.
போட்டீங்க சார் எல்லாம்
கூகுளில் டைப் பண்ணி பார்த்துக்கிறேன்.
கால்குலேஷன் போடுறதுல சிரமப்பட்டு போட்டுருக்காங்க.
கூகுளில் போட்டு நெட்
கூகுளே அடிச்சா
போட்டதுதான்.
சார் பேக்ரவுண்ட் எடுத்துக்கலாம். பேக்ரவுண்ட் தானே
99.9 வருதா?
ஆமா.
எடுத்துருமா?
121 வந்து பேக்ரவுண்ட் வந்து 34 கவுண்ட்ஸ்.
34.
ம்.
கவுண்ட்ஸ் டைம் சார்
அது அதே தான் சேம்.
அதேதான்.
60.
எல்லாம் 62 டைம்.
அதுக்கு அடுத்தது வந்து 290
344 சார்.
344 எடுத்துக்கலாமா?
அதான் நமக்கு எடுத்துக்கலாம்.
21 கவுண்ட்ஸ். 344 அதுக்கு 20 ஆமா.
Next is the
352.
352.
23 counts. Then 1275.
இல்ல வேண்டாம் எல்லாம் TV 1214. The cross counter, you will be type 60%. The comma competency will give 6. Efficiency கண்டுபிடிச்சோம் முன்னாடி வந்து எலிமினேஷன் our இது வந்து எனர்ஜி இந்த கவுண்ட் 352 ஒரு 4 பேர் காப்பி எடுத்துட்டு ஆமா சார் பேக்ரவுண்ட் மைனஸ் சாரி efficiency அது கரெக்டான efficiency Thanks. எவ்வளவு பேப்பர் வேணும் நான் Just I'm very busy.
அதுல பெரிய error வராது.
நேற்றுக்கு கால் பண்ணி வச்சு நியர் பை வேலை சுற்றி எவ்வளோ கஷ்டம் இருக்கு நான் உட்காந்துருக்கோம்.
ஜீரோ ஜீரோ ஒன்று தான்.
ஆமா
ஃபார்முலா கரெக்ட் பண்ணிட்டாலே பாதி மார்க் வந்துச்சு. எஃபிஷியன்சி பர்சன்டேஜ்
அப்போ அது போடக்கூடாது.
ஆமா சார், அப்படின்னா அது அந்த இது 100 மேல 100 100 இது 0.28 இல்ல இங்கேயும் 100 அதான் சார் சார் இது 0.28 போட்டுக்கலாம். அது
இப்படியே இருக்கட்டும்.
இருக்கட்டும்.
காசு நல்லா பார்த்துக்கோ.
அது 10,000 மல்டிபிள் சொல்லக்கூடாது. கரெக்டா? இல்லை 10,000 இல்லை, ஏன்னா இது ஒரு ஸ்பெசிஃபிக்காக சொன்னாங்க. என்ன இது வந்து பர்சன்டேஜ் போடுறப்போ இது பாயிண்ட் பார்த்து அப்படியா? ஆமாம், இவ்வளோ நேரம் கேட்டோம்னா சரி, இந்த ஃபார்முலா கரெக்டாக
எல்லாமே 0.000 வருது ஆன்சர். அதான்
இல்லை, இங்கே 10,000 போடணும்.
இந்த எஃபிஷியன்சி இருக்குல்ல, இந்த மாதிரி நீங்கள் நம்பரில் போட்டிங்கன்னா இது பர்சன்டேஜில்.
சரி,
ஸோ எப்பவுமே இந்த மாதிரி நீங்கள் போட்டிங்கன்னா மேலே 100 போட்டுக்கணும். இல்லைன்னா வச்சுக்கோங்க 0.28 போட்டு போயிடுது.
சரி, இதுக்கு
அதே மாதிரி இதுவும் தான் ஃபீல்டு இந்த மாதிரி நம்பரில் போட்டிங்கன்னு வச்சுக்கோங்க 100% போட்டிங்கன்னா மேலே அதாவது நான் போடும்போது என்ன பண்ணி ஈஸியாக இருக்கும். போடும்போதே 0. somethingல போட்டு போட்டிங்கன்னா உங்களுக்கு வராது, பிரச்சனை வராது.
திரும்ப 10,000 மல்டிப்ளை பண்ணிக்கணும். 100 into 100 அவ்வளோ. எங்கேயாச்சு சார்?
முதலுக்கு என்ன சார்?
0.001. அதான் 10,000 மல்டிப்ளை பண்ண தெரியும்.
ஃபர்ஸ்ட் இது பாயிண்ட் 1 இருந்துச்சு.
அதான் சார்
09 and 1 20
1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2 3 1 2
First is that. Second is 9.3.
1764.
Kilo Bekura, madam. தெரிஞ்ச விஷயத்தை போயிட்டு என்ன சொல்றீங்க? என்ன எடுக்கலாம்னு என்ன சொல்லிட்டு
செக் பண்ணிடுறேன்.
அதான் சார் நான் என்ன பண்ணிருக்கேன் கரெக்டாக ரொம்ப டிஃபரன்ஸ் அந்த இந்த போட்டு இப்போ வந்து நான் அதுதான் இப்போ வந்து இதுக்கு பார்த்தீங்கன்னா
கொஞ்சம் எஃபிஷியன்சி போடணும். 1.5
No, there is a percentage of error, but it's almost.
Madam, no,
And tomorrow's exam will be with us. You have to tell me the radian nuclei.
European 152, 121. That is the 12.3. Alpha channel is 344.5. European 152. That is 9.3. And then 214. 5.92.
Sodium 22.
Sodium 122. 127. That is 7.1.
That is very, very less.
Because of this efficiency now, we are taking that yearly.
Yeah, if you take that, this is actually the standard deviation.
Then we reduce the
English
this.
how much?
Because in the
But the thing is, you need to plot.
No, next year we will not come.
Software எல்லாம் select பண்ணணும்.
The thing.
சரி இது போட்டு பார்க்கணும். அதெல்லாம்
அவங்க தண்ணி வச்சிருக்காங்க.
இந்த நம்பர் போடுறதுனா கிராஃப்ல
அதெல்லாம் பண்ணினா
Efficiency is equal
எல்லாத்துக்கும் மட்டும் தான்
0.2.
GIAN இருக்குது.
Everything you want.
Madam.
This is the PDF format, right? Nowadays.
Yeah, it is.
Wi-Fi இருக்குது. ஏரியாவையா?
ஆமா
Online software, yes, right? You need original. You need to put the
but it is asking that
here no Wi-Fi is there. It's only answer. It's of no use. One or 2% of yeah.
யூனிவர்சிட்டி நாங்கள் மெயின் போன ஆகிட்டோம். ட்ரை பண்ணிட்டு இருந்தேன்.
சார் ஆன்சர் சீட் நான் தான் கொடுத்துருக்கோன். என் கை வாங்கிட்டே இருக்கேன். சார் இதில் மாஸ் கம்பெனி
ஆட் பண்ணால் அது
இது மேடம் இங்கே காடல் மூட்டை அதுக்கப்புறம் 2 நாள் கொடுத்துருக்கேன். 3 இருக்கு இப்ப 2 கொடுத்தேன். அப்படியா? ஒண்ணு எங்கேயும் காணுங்க. சரி எஃபிஷியன்சிக்கு அந்த ஃபார்முலா அப்புறம் அது கூட ஈல்டுனா ஐ இன்னொன்னு ஃபார்முலாவை கொடுங்க. இதுதான் 500 milligram வந்து அதோட weight. கிராம் கணக்குல பண்ணா